Today we're talking about common bonding patterns of the elements we normally see in organic chemistry: hydrogen, boron, carbon, nitrogen, oxygen, and our halogens, which we are going to denote using this X here. So each of these elements has a common bonding pattern, what you traditionally see when they bond with other molecules. And this is depending on their valence electrons. And those are, again, those electrons we find in their outermost shell. And each of these elements has a different number of valence electrons. Hydrogen, for instance, has one valence electron. And that valence electron is in the 1s orbital, remember? So 1s orbital, it can only hold 2 electrons. So hydrogen is hanging out here with its one valence electron, and it wants to be filled. It wants to have 2 electrons total. So we notice that here it has the capacity for a bond. So this is what's going to link it to another molecule or element. So if we have another hydrogen come in with its one valence electron, boom, here we have 2 electrons together and they form a bond between these 2 atoms. That's a covalent bond, and it would be depicted like that. But when we're talking about common bonding patterns, all we're going to say is that hydrogen has a capacity for 1 bond here, and that's how we normally see it. Now boron has 3 valence electrons. It does something a little bit funky. You know, we all the time we hear about this octet rule where we know elements want to have 8 electrons in their octet, in their outer valence. That does not include hydrogen. But boron actually has only 3 valence electrons. So it's actually not too concerned about getting 8. It really just wants 6. And that's because it's wanting to fill up these 3 open bonding positions that it has, stemming from these 3 valence electrons. So in its neutral state, boron is only going to make 3 bonds. Now let's talk about carbon. Carbon, we know, has 4 valence electrons. This is like our heavy hitter in organic chemistry. So we're going to dot them around here, 1, 2, 3, 4. And we have 4 open seats for bonds. So that means that carbon, we're going to see it make 4 bonds. Now the next one we have is nitrogen. Nitrogen has 5 valence electrons. Let's start with our Lewis structure. 1, 2, 3, 4. I'm going to put the 5th one down here. So in nitrogen, you're going to see 1 completed lone pair. That means that there is no bonding able to happen down here. But we do have 3 areas where we can create new bonds. And so you're going to see nitrogen with 3 bonds and 1 lone pair. Now oxygen is our next. It has 6 valence electrons. Sorry I put that so far down there. And let's do our Lewis structure. So we have 1, 2, 3, 4, 5. And I'm just going to throw this last one down here. And so notice we have 2 sets of lone pairs. So there's no bonding able to happen right there. But what we're going to do is pull these out, and oxygen can have 2 bonds. And then finally we have our halogen. And halogens have 7 valence electrons. So we can figure this out easily from our Lewis structure. 1, 2, 3, 4, 5, 6, 7. Notice these lone pairs are all taken up. We can't do anything there, but we have the capacity for 1 bond here, and that's in its neutral state. So then let's talk about, these were uncharged. These are neutral. And let's talk about, let's do our negatively charged over here. So remember, when we're negatively charged, that means we're adding 1 electron. And that brings about a negative charge because we have more negatively charged subatomic particles now, electrons, than we do protons. And remember, normally in our uncharged elements, the number of protons equals the number of electrons. So it balances out. But now, since we're adding 1 electron, we have a negative charge. This is called an anion. So for hydrogen, let's see if we can actually move this up a little bit. Boop. Okay. Nice. Coming back around. So, for hydrogen, we're going to now have 2 electrons because we had 1 valence before, so now we're working with 2 electrons. So it's going to go like this. And this hydrogen is not going to have the capacity to bond with anything. So this hydrogen, when it's negatively charged, it's full up. Now let's talk about boron. Now boron, when it's negatively charged, we now are working with 4 valence electrons. Compare that to our 3 that we have over here. So boron does have the capacity to have 4 electrons, and guess what? It's going to have 4 bonds. And we're going to put a little negative sign here to indicate that this boron is negative. Carbon. So now we're working with 5 valence electrons. We added 1. So we're going to do our Lewis structure. 1, 2, 3, 4, 5. Notice there's no room for a bond here. And so now we can pretty easily say carbon, when it's negatively charged, has 3 bonds and 1 lone pair. We're going to denote that with our little minus sign here. Now nitrogen. Nitrogen, when it's negative, has 6 valence electrons. So the 1, 2, 3, 4, 5, 6, throw it up there. Notice again, we have 2 lone pairs, or 2 sets of lone pairs, and 2 places where we're able to make bonds. And if you check this out, it's the same structure as oxygen. And if carbon, check this out, it's the same structure as nitrogen. This carbon is the same structure as this boron over here. So it's kind of an interesting dynamic that we have going on. Oxygen, we're going to add 1 electron, 7 valence electrons. So now we have 1, 2, 3, 4, 5, 6, 7, and we only have 1 position for a bond. And then finally, when we have our halogen, we now have 8 valence electrons. That's our magic number, right? So we already know there are going to be no bonds here. This now has a noble gas electron configuration. So it's all set. It is negatively charged, but it's not going to want to do much else from here. So those are our negatively charged versions of these elements. Now let's see our positively charged. And what happens when we positively charge something? What does that mean? It means we're taking away 1 electron. And so that means there's going to be more protons in the nucleus than there are electrons, which have that negative force to balance out the positive. So it's going to have an overall positive charge. So we're taking away an electron. So for hydrogen, we only started with 1 electron, right? So what is this going to look like? We're going to just take it away. It's just going to be a proton. It's almost not even hydrogen anymore. It's literally just a proton. So we have 0 valence electrons. Now boron surprisingly doesn't have a positively charged form. So we're just going to kind of ignore this. Just know it has its neutral form and it has its negatively charged form. We don't need to worry about this positively charged boron. It's a little funky. It doesn't really happen. Now carbon. So we went from 4 valence electrons. Now we're taking it away. We're going to have 3 valence electrons. So we go 1, 2, 3. We can see that that's 3 bonds. And make sure we put our positive sign here to indicate the charge. Nitrogen, we're taking away 1 of these 5 valence electrons. Now we have 4 valence electrons. 1, 2, 3, 4. Boom. We're going to make 4 charges, or 4 bonds. Oxygen, we now have 5 valence electrons. So we're going to go 1, 2, 3, 4, 5, and notice that we can make 3 bonds. And then finally we have our halogen. We went from 7 valence electrons. We're going to go down to 6 valence electrons. What is this going to look like? We're going to do 1, 2, 3, 4, 5, 6. And that's positively charged as well. So now we know our common bonding patterns for neutral, negatively charged, and positively charged versions of all of these elements. One thing I do want to point out before we end this video, though, is that you might see these a little bit different than what we're seeing right now. Something that you might see with nitrogen, for instance. We know that nitrogen in its neutral form has 3 bonds and 1 lone pair, right? And what we were seeing was this nitrogen like this. But you know what you can see sometimes? Is nitrogen like this. Or nitrogen like this. You know, we can have these 3 bonds and 1 lone pair in different ways. And we can see the same thing with oxygen. We know that oxygen has 2 lone pairs and 2 bonds. So guess what? We're not always going to see it like this. Sometimes we're going to see it in the bent structure. We're actually going to see it in the bent structure a lot because guess what? That's water. And we also sometimes see oxygen with a double bond and then it's 2 lone pairs out here. So just know these patterns that we reviewed today, these are going to show up in different ways. But if you just take a peek at this, this is kind of how they show up in general. And this should give you some great new information. Sorry, I can't zoom in and out the way I want to, but next video I'll make sure that I can show everyone everything all at once. So hope this helped. My name is Ben, and thanks for watching.